Good morning. Today we're going to be talking about the fundamental theorem of algebra. The fundamental theorem of algebra states that any polynomial p to the z is equal to the sum as v equals 0 to n of av, which is a constant, z to the v, with n greater than 0 and a to the n not equal 0 has n roots. The Liouville equation allows a proof of Gauss's theory. It states that 1 over pz is analytic and bounded as the absolute value of z goes to infinity, which by Liouville's theory calls for p to the z to equal a constant. This allows p to the z to have at least one root lambda. Now, if we took this root and we divided it into the polynomial p to the z, depending on the degree of the polynomial, we would end up getting more roots. I'm just going to go down here, guys, for a minute here. And we'd continue dividing the polynomial until we reduced it to a degree of 0. So what we're going to do now is we're going to take a look at what these roots would look like. And we're going to do this by looking at graphs. So, for example, if we looked at these two graphs here, we would realize that the first graph is a third degree polynomial, and it has 3 real roots. And the second polynomial there is a fourth degree polynomial, and it has 4 real roots. Now, if we go down and we look at these two graphs here, according to Gauss's theory, the fundamental theorem of algebra, that first cubic there will also have 3 roots, even though it only crosses the x-axis one time. And the answer to that is that 2 of the roots are actually complex. And if we look at the fourth degree polynomial, it doesn't have any real roots, but it's assured to have at least 4 complex roots. Now, the question here is that why does the first graph have 1 real root and then 2 complex roots, and why does the second graph have 4 complex roots? And the reason why is because that the complex roots have to come in pairs because they're conjugates. So we kind of come down here, and we're going to finally finish this discussion out by talking about an application of complex numbers. But before do that, let's just kind of sum up here. So Gauss's fundamental theory of algebra really introduces the idea of complex roots and opens up the complex plane so that we're not just working in the real plane now, but we're also working in the complex plane. That leads to a lot of applications in physics, and one of the applications that we're just going to discuss briefly is radio telescopes. Now, radio telescopes receive signals as voltages, but when they collect these voltages, it goes into large 2D arrays, and this data is collected as complex vectors. Now, what's really cool about these radio telescopes is that if the signal is earthbound, the array is not filled. But if the array comes outside of the Earth, that array is filled. So that's kind of cool. And there's a little site there that, if you take a look there, you could read the article on it. I think it's pretty neat. And that's all, guys. Thank you so much now. Bye now.